kind of like, I don't know, admin stuff at first. It's the last lab. So I just wanted to thank you guys because you like, so I also take like a grad course in this topic, and you guys have asked incredible questions that like make me think about the material in a different way. And also you guys are just great in general. Like I think I mentioned it like at the beginning, like how I try to be like relatively not harsh, but like I don't know, I guess harsh with like the lab grading in the beginning, and like it has totally paid off because you guys are killing it like in the last in the second half of the semester, so that's awesome. Um, what was the other thing I wanted to say? I guess just point out the uh, this announcement I made. I like really value your opinions on like how I can teach better, and just do better in general in the course, or what you liked and what you didn't. And I guess I just didn't really understand that I could do this. But I guess Rich said that like it's totally up to us how we do everything. So I can see like how like what the response rate of different like these evaluations is. So I'm going to do the same thing that Rich mentioned with where is it? Oh, these are all my announcements. But he mentioned the same thing with the other PhD, Drew Rosin's stuff, that if you get to like 50%, you can increase your overall grade by a point. So I'm just going to do the same thing. I didn't know I could do that before. So just, an opportunity to get extra credit and just help me improve for, the future. So let's get to it. This is a fun lab. It's a little bit more of a departure from the stuff that we've been doing. Like last week, we made that connection between waves and electric fields, and why suddenly we're talking about lasers and waves and refractance and all that. And in this week, we're just kind of extending that lasers and waves and all that good stuff. So I'm just going to go kind of chronologically because the background is quite scattered. So if at any point during this, I guess hold on, I'll put the floating meeting controls up there so I can see if anyone puts anything in the chat. But the background is quite scattered, so I felt that I was being quite scattered on Monday when I went through this. So if any of this is super confusing, just tell me to pause and I'll do it slowly or go through something a little bit more. Put that down here so I can see everything. Okay. So the first thing that we can talk about, I think, let's see, what's the easiest way to start? I guess the easiest way to start would be with whoa, how did that happen? Oh my God, did anyone else see that? I saw something on my screen. Nino just like messaged me and it came up not in the chat, but like on my screen. I don't know how Nino did that, little hacker over there, but that was hilarious. Um, so let's start off with this thing called, I guess in the English pronunciation, it would be Huygens principle. If you want to say it in Dutch, this is like an ow sound, and this is like a h, so it's like the Huygens principle. And it tells us if waves are going through some kind of obstruction. So the easiest way that we can think about this is thinking about light as waves. So imagine that our laser beam is not kind of this infinitesimal thing that's going through, but rather kind of like waves from like the ocean. And say you put some obstruction in the ocean, like I don't know, like two walls, and what happens with this gap in the ocean. So what happens is based on this Huygens principle is that every point on this obstruction now becomes like its own source. So instead of the source being like the ocean driving these waves in, now because of this obstruction, you have new sources. And this not only happens with gaps. So this is, this slit interference, double slit, single slit interference that you see, um, you know, characteristically in some of the textbooks and stuff. This is chapter 4 of the that Giancoli textbook you guys use. And another textbook I'm going to reference that I think is does this in the most the easiest way was something that I used when I was studying in college, called Conquering the Physics GRE. This is chapter 3 of theirs, where they use something called the phase difference. And I found that to be the easiest way to go about that. But we'll go back to this in a second. You'll be doing this in part 3 of the lab. Here we go. So this double slit interference thing. So what's happening with these slits is that you have this beam of light coming in, and light, because it's behaving as a wave in our experiment here, it is coming through and hitting this obstruction, and at every point on this obstruction, it kind of makes a wave. So that's what that Huygens principle is. But something really cool happens when we replace that slit. So instead of a slit, so this, imagine you have a beach and like an infinite wall and an infinite wall. If instead you replace this gap with an obstruction, like you have here, the same thing happens. It's like in reverse. So weirdly, what we're going to be doing in this lab, I thought I was reading the lab manual wrong, but we actually use a piece of our own hair. So instead of closing something and sending light through a slit like that, we're going to have emptiness, and then we're going to put a single piece of our hair, and the light is going to hit the hair, and all these, the hair is now in many ways the source of the light. So the light hits, this is just I don't know, some obstruction. So imagine this gray thing is our hair, and then the light hits the hair, and at all the pieces of the hair on the edges of the hair, now the light comes in. So I thought this figure was probably the best way to go about that. And what we see is interference, and this is kind of characteristic of waves. So let me go over to wave interference. So this is kind of called the superposition principle. It's very similar to when we were doing 133, when we had that standing wave. If you view the wave as like that, sending like a whip down the hose as a kid, it comes back if the wave going in is the wave that's coming out. So that's constructive interference, where these things add up together. Destructive interference would be if the waves cancel exactly. I'll be a bit more mathematical about that in a second when I open up this program down here. One really cool thing that I just want to touch on, and the reason I say that this kind of goes one step further away from the waves and the stuff that we have been talking about, like the electric and magnetic field, is that light and even electrons and stuff like that have very weird properties, that not only do they have these interference properties, but this is kind of the backbone of quantum mechanics. If you observe it, weird things happen. So I just wanted to play this illustration for you. That's kind of one thing that we could do with this experiment if we had a bit more time, was to set up something that illustrates why quantum mechanics is weird. So imagine that if you're sending this machine with a bunch of particles, these particles don't interfere like this. They aren't waves. So if one particle is going one way and another one is going the other way, it's not like a bigger particle happens. So you see in this interference here, if these two waves are at the same value, they add. Similarly, if they're in opposite values, they cancel. That doesn't happen with particles. So if you let this, I don't know, baseball shooter machine go, it just produces a random assortment of particles over here. However, if it's a wave, Here we're seeing that Hawkins principle. So here, when the wave goes into this slot, now this slot is acting just like that emitter here. So this slot is emitting a wave, and this slot is emitting a wave. And let's see over here, some of these waves will interfere with each other. The waves over on this side, they won't interfere with much because, you know, it's kind of like that parallel plate capacitor. The things on the end won't have as much effect as things in the middle where they're interfering with everything. So we'll get this giant peak in the middle and some smaller peaks as we go out. And that's the wave behavior. However, light, electrons, and everything else behaves as both. And so this is kind of the weirdness of quantum mechanics. We won't get into it at all in this lab. I just wanted to kind of explain to you, what the implications of what we're doing today are. So you can see that as the thing is going through, it is behaving as a wave. However, as soon as it interacts with its environment, it behaves as a particle. So it's kind of behaving as both things at once. And now you can see that if we observe the behavior, it's our observing something is kind of like it interacting with the environment. So that little eyeball there, the observer, was the wave-like nature collapsing, the particle or the light becoming a particle, and then behaving as no interference on the wall. So that's kind of the deeper implications. There are a million ways to interpret this, and it goes into something called like interpretations of quantum mechanics, where you can, some people say that it went through both holes at the same time, and that's kind of the origin of the many worlds hypothesis, where you made one decision and now you're splitting off into a million different lives. The most kind of accurate mathematical way to think about this is all in terms of probabilities. So until you observe something happening, you only know about it in terms of probabilities. Sorry for the tangent, but I thought it would be cool to kind of place what we're doing in a greater context of historically how things happened. So that's what they're talking about in this textbook. This textbook does do it in a kind of nice way. So when I say do it, I mean they derive this equation here. So this equation is saying, let me state it over here. I think it's much nicer, much more nicely stated in this book. It's talking about the constructive interference or destructive interference. So if you take a look at these forms of the wave, so this is a wave traveling in the x direction, and it's got this frequency or speed omega. Two different things. So we have one wave f and one wave g. And this pi here is kind of this phase shift. Let's see if we can get a picture of it. I'm sure it's over here somewhere. Yes, they relate this phase shift to the distance that the wave will travel. So here, because these two things, so note that I'm deriving this in the two slit case. What we'll be doing in class is actually the one slit case, which I guess the absence of one slit are notably our hair. But the kind of everything kind of holds in the same way. You just have to make a little bit of different assumptions. It's just much easier to derive things when you have two slits. So the reason it's easier to derive is you have a exact location at which this wave is coming from and an exact location at which this wave is coming from. Whether or not they constructively interfere or destructively interfere, you know that they end at the same spot. So if you use a little bit of trig or geometry, you can tell that the difference between these two path lengths is given by this. And so that's why they make that comparison here between path difference, delta x. And so what ends up happening, it constructively interferes, and I'll zoom out on this because I think this page is the most helpful. Again, this is for two slits. What ends up happening is constructive interference happens when things are at integer multiples or half integer multiples, and it flips for destructive. And just to illustrate what we mean by this kind of phase difference down here, I'll pull up this program right here and plot some cosine functions or waves. So if I were to plot two waves, let's say, let me just figure out which one is which. So this blue one is this equation, and the yellow or orange one is this equation. So that's a normal cosine function. It's starting at 1, coming down here. And this guy here is that delta, the phase shift, or the phase difference. So what ends up happening is if things are at, let's follow what they're saying here, constructive interference, if there is a 2m. So m is an integer. That means 2m is an even number. So let's see what happens if I do 2 pi. Exactly equal. And I can prove it to you by just doing a little bit off. See, that's a little bit off and a little bit off. But if I do exactly 2, they're both right on top of each other. Now, let's show that destructive interference happens with odd integers. Let's say I do 3. Now what's happening? One of the waves is at its maximum and its minima, and the other is exactly opposite. So both of these are going to add and give me 0, hence destructive interference. And so that's what these dark fringes are going to be on the pattern that looks like this. Let's see what else I'm missing here. So notably, one thing that you're going to use in this lab is that this equation for the single slit occurs for the minima. So for instance, with this picture, the distances that you're going to measure are these things. So you're going to measure from 0 to this gap, and this gap. So it's always the minima. Here's kind of a schematic to show you. What you're going to end up doing is having a hair placed to this thing, a laser going through. You're going to have a central maxima, a bright peak in the middle, and then you're going to have these kind of less bright things going off. And what you're going to do is measure the dark peaks. So you're going to measure the darker peaks, which are kind of these gaps in between the bright lights. Just to make it easier on yourself and to reduce error, you're going to measure that to that, and then you're just going to divide by 2, because that would end up being, this distance to there. But really, you're going to measure here to here and divide by 2. Let's see what else I'm missing here. This I'm going to derive on the board. And part 1 and 3 in the lab are quite, I guess, qualitative in the sense that you're really just going to be looking at trends and what happens with polarization. If you look at like the part 1 and 2, it's basically just filling in answers, whereas part 2 is like, quantitative. So you're actually doing numbers and doing some math and stuff like that. Whereas 1 and 3 are more just observing what happens. Notably for 3, I just wanted to point out, because they don't explain to you why what you're seeing is happening. And this phenomenon is known as Malus Law. It's where you have your electric field is polarized, and if you put a polarizing sheet in it, it changes the polarization of your wave. And in particular, this paragraph right here explains exactly what is happening when you put more than one polarizer in sequence with each other. So for instance, if your light is just arbitrarily polarized and you put a polarizer that is preferential towards this direction, only things in that direction will go through now. So now if you put another polarizer like that, nothing will go through. But the really weird thing is if you put a third in the middle of them, you will see stuff at a certain angle. And that paragraph explains it quite nicely. So let's get out of here. And I just wanted to explain the measuring device you're going to use, because it's quite wonky. I don't know why we don't have like the calipers that you usually use. I'll explain it more like when I have it physically in front of me. But what ends up happening is you put this black offset of 25 millimeters into this thing. So this will not close anymore. Like you can't go all the way down to 0. It's annoying, but what the result of this is that once you put this block into here, let's see if they have a picture of it. Some of you do have ones that go all the way down to 0, but I think the labs in the room that I'm not in have it, the annoying ones, like this. So what ends up happening is that this, your normal origin, is not where you're going to be measuring from anymore. You're going to be measuring from 25 millimeters. So this is your 0. You're going to unscrew this thing a little bit and rescrew it, and whatever is in between here, you'll get a measurement. In terms of what these numbers on the side of it mean, I determined it like the following. These numbers, they go from 0 to 49. And what I realized was if I unspin it twice, so if I spin this dial twice, so 0 to 49 is 50 numbers, so that means I'm experiencing 100 numbers. If I spin it twice, I go from 25 millimeters to 26 millimeters. And so if I have 100 numbers, I divide 1 millimeter by 100, and then I get 0.01 millimeters. 0.01 millimeters. And then I change that to meters, and I know that 1 dash on my micrometer, something like that, is it's not actually a micrometer. So that's one point of error that you can make quite easily. The units aren't actually 1 to the -6; they're 1 to the -5. So that's just something to be warned about, because I made that mistake when I was doing it. Other than that, I will get to the board and start deriving stuff, and I will send this recording soon. Any questions before I start running around? Okay, I will stop recording and start running around.